Right. The topic of today's lecture is Stefan-Boltzmann law of blackbody radiation. So we'll be discussing how much energy, okay, will be radiated by a black body which is at a certain temperature. Okay. And as we know, black body is an object which absorbs all the radiation incident on it. Okay. We'll be talking about absorption by a black body and also emission by a black body. Okay. Uh, Consider this situation first. Suppose there is an object, a real life object only. Assume it is at room temperature, some real life object at room temperature. In fact, let's consider two objects, not one. One object which is black, okay, which appears black, and another object which could be of any color. It may be a very shiny object also. Okay, very shiny means highly reflective object also. It could be. So just a moment. Let's consider something of yellow color. Right. Assume these two objects are in a room which is at a temperature of 25 degrees C. The room temperature is 25 degrees C. Let's say the objects are also at 25 degrees C. Okay, the black colored object is at 25 degrees C and the yellow one is also at 25 degrees C. Okay. Now, any of you tell me from your everyday experience, if there's an object at room temperature and you leave it open, will it continue to stay at that temperature or will its temperature change? I want answers from all of you. Type your answers in chat. An object is already at room temperature and it is left open in the room. Will it continue to stay at the same temperature or will its temperature change? Think carefully, answer in chat. Okay, I got three answers saying there will be no temperature change. If the room temperature does not change, object temperature also will not change. Okay, and that is correct. This we can observe in daily life also. An object which is open to the room, you don't see it cooling on its own or you don't see it heating up on its own. Fine, its temperature remains equal to the room temperature. It will be in thermal equilibrium with the room. Okay, fine. Now 25 degrees C in Kelvin, if you see, it is around 298 Kelvin. Okay, definitely it's a temperature more than 0 Kelvin. Okay, so both these objects will be radiating. Any object at a temperature more than 0 Kelvin will definitely radiate energy in the form of electromagnetic waves. Okay, thermal radiation will be there. So these are two radiators now. Okay, and you all tell me, will there be energy falling on these objects also or not from the surroundings? Definitely, they are open to the room. The walls of the room or the other objects in the room, their radiations will be incident on these objects as well. So, on both these objects, there is radiation incident and also there is radiation emitted. Fine. This happens with all objects, not only these two. Whatever objects are there in the room, they will both be receiving, receiving as well as radiating energy. So some incident energy will be there on them. Okay, not only in this direction, it could be in any direction randomly. I'm just showing you that there will be some energy incident on them. Okay. And there will also be some energy radiated by them. Okay. Now, one of you tell me, or any of you can tell me, which of these is a better absorber, the black object or the yellow object? Let's assume only visible radiation is incident. Which of these is a better absorber? Let's name them as A and B. This one is A, this one is B. The black object is a better absorber. Okay, it appears black because it is absorbing all the visible radiation. Okay, the other one appears yellow because it is reflecting yellow. Other colors it is absorbing, but it is reflecting yellow. Okay, so the black one is a better absorber. In general, a darker object is a better absorber of visible light than a brighter object. Okay, so the object A here is a better absorber of energy. Fine. Now, energy is incident on both of them from the surroundings. A is a better absorber. Now, if anything absorbs energy, if an object absorbs heat, what should happen to its temperature? Its temperature should rise. Okay. Now, A is absorbing energy, B is also absorbing energy, but A is a better absorber. Means its temperature has a tendency to rise quicker than that of B. Okay. Definitely, because if it's absorbing more heat, then obviously its temperature tends to rise faster. Okay, let's assume their mass is same, specific heat is same, just their colors are different. Fine. Of course, heat can be related to temperature change through mass and specific heat. Delta Q is equal to ms delta T, obviously. So it depends on mass and specific heat also. Let's assume those are same, only the colors are different. Okay. So its temperature has a tendency to rise quicker than that of B because it is absorbing more heat, or it is absorbing heat more rapidly than B, or it is absorbing radiation more rapidly than B, better than B. Okay. But we see that, okay, from everyday experience, we see that both objects maintain the same temperature. Whether it's a dark object or a very shiny object, if it is at room temperature, it will continue to be at room temperature. That we can observe in daily life. Now, A is a better absorber. Means of the energy incident on A and B, A absorbs more energy. So A's temperature should rise faster than B, but it maintains the same temperature. Now, first of all, either A or B, how are they able to maintain the same temperature? Because they are radiating also. Okay, they are absorbing and also radiating. Now, these processes, absorption and radiation, are completely independent of each other. Whether an object absorbs or not doesn't matter. If its temperature is more than 0 Kelvin, it will radiate. Okay. And whether and how much an object radiates also doesn't matter. If energy is incident on it, it will absorb. Okay. Radiation depends on the body's temperature and surface area. We'll discuss in Stephen's law anyway. So radiation depends on temperature and other properties of that body itself. Absorption depends on how much is being incident on it. It depends on the surroundings, kind of. Okay. And remember, absorption and radiation are completely independent of each other. Now, there is energy incident on these objects. There is energy being radiated by these objects also. They are maintaining constant temperature. Okay. So the answer to will the temperatures change is no. That means they absorb and radiate at the same rate. How much ever they are absorbing in a certain interval of time, the same amount of heat they must be radiating also. That is why their temperatures are not changing. Okay. Now, out of A and B, A is a better absorber. Its temperature does not change. That means A should be a better radiator as well. Okay. I'll give you an example. Suppose there are two objects A and B. Let's say some 200 joules of energy is incident on them in a certain interval of time, maybe 1 second, 10 seconds, whatever it is. The interval is not important here. In equal intervals of time, let's say 200 joules of energy was incident on them. Out of 200 joules, let's say A has absorbed 150 joules. Okay. Whereas B has absorbed only, let's say 80 joules. A is a better absorber than B. So out of the energy incident on them, A absorbs more compared to B. Okay. Now A has to maintain, not has to, we observe that A maintains its temperature and B also maintains the same temperature. Then for that to happen, A will have to radiate 150 joules in the same interval. Otherwise, its temperature will change. Okay. And B will have to radiate 80 joules in that interval. Otherwise, its temperature will change. So how much ever energy was absorbed, the same amount of energy must have been emitted such that the temperature remains same. So what do we understand from all this? We understand that better absorbers are better emitters as well, better radiators as well. Fine. So a good absorber means absorber of radiation, okay, is also a good emitter at a given temperature. Is this clear to all of you? We are using this idea that an object at room temperature continues to be at room temperature to prove this. Okay, we take two different objects whose absorptive powers are different, and both of them tend to maintain the temperature. That means both of them should be emitting also proportional to their absorption. So if an object absorbs more, it should be emitting more to maintain its temperature. If an object absorbs less, it should be emitting less to maintain its temperature. Okay. Now, suppose there is a black body. As I said, it's a hypothetical object. They don't exist in real life. We can create objects which are close to black bodies. Okay, but a perfect black body does not exist in real life. But consider a black body. Okay, scientists and mathematicians, they can work on hypothetical objects also. Like theoretically, they can tell what will happen if such an object exists. Okay, so Stefan-Boltzmann's law tells us that only. If a black body exists, okay, let's say at a temperature T. This is absolute temperature. Absolute temperature means temperature in Kelvin. Okay, let's say there's a black body and its surface area is A. Now we know that any object at a temperature more than 0 Kelvin will be emitting radiation. So a black body at a temperature T having a surface area A, what happens is the rate of emission of heat. Okay. Mathematically, rate of emission of heat is written like this: d capital Q by dt. Okay. Capital Q stands for heat, T stands for time, small t stands for time. The rate of emission of heat by a black body through radiation. Okay. We are talking about radiation now, not conduction and all. It is proportional to, first factor is the surface area of the object. Why? Because radiation means energy leaving from the object, takes place from the surface itself. And keep this point in mind, objects radiate because of molecular vibrations. At any temperature more than 0 Kelvin, molecular vibrations will be there. So radiation will definitely happen. You cannot prevent that. Fine. So where does energy finally leave the object from? Surface only. And more the number of molecules on the surface, more the energy radiated by the object. Okay. So rate of emission of heat through radiation is proportional to surface area of the black body. Okay. And it is also proportional to the fourth power of its absolute temperature, means temperature raised to the power 4. And obviously there will be a proportionality constant. So if you put all this together, the rate of emission, okay, dq by dt emitted by black body is equal to the proportionality constant is called Stefan-Boltzmann constant, or sometimes they just call it as Stephen's constant. The law also, sometimes they just call it as Stephen's law. Stephen's law, Stefan-Boltzmann law, or Stephen's fourth power law, they are all the same. Okay, is equal to sigma A. A stands for surface area and T to the power 4. So if you know the temperature of a black body, you can tell at what rate it emits heat through radiation. Okay. And the value of Stephen's constant, you don't have to memorize this, is 5.67 into 10 to the power of minus 8 in SI units. Okay, so Q stands for heat emitted through radiation. So therefore dQ by dt, that is nothing but rate of emission of energy in the form of radiation, is equal to sigma A T power 4, and this is valid for a black body. Okay, using this equation, I want you all to derive the SI unit and dimensional formula of Stephen's constant. Okay. Do this, all of you. Okay, it's quite simple. The quantity on the left hand side of the equation, dq by dt, heat emitted per unit time. Now, heat is a form of energy. So, left hand side is basically energy per unit time. Energy per unit time is nothing but power. Okay. So, left hand side, the unit is watts, is equal to sigma's unit, we don't know. Area will be in meter square. Temperature is in Kelvin definitely. So, Kelvin to the power 4. So, sigma's SI unit, okay, the SI unit of Stephen's constant becomes watts per meter square per Kelvin to the power 4. Okay, this is how it will be written in the questions or textbooks. And dimensional formula. Left hand side is energy per unit time. Energy is ml square t power minus 2 divided by time becomes ml square t power minus 3. Okay. So left hand side is ml square t power minus 3, that is power, is equal to dimensional formula of Stephen's constant is not known. Area is L square. So L square can be cancelled. Then temperature to the power 4 is K power 4. That's all. Therefore, the dimensional formula of Stephen's constant becomes m t power minus 3, and K power 4 goes to the other side, becomes K power minus 4. That's all. It's very important to know how to derive unit and dimension of a quantity based on a formula. Okay. Every year in the final exams that you are going to take, you will definitely have questions based on dimensional analysis, deriving units, or using these dimensions in equations. Okay, they may give you a set of quantities and ask you which quantities have same dimensions, or the product of which quantities gives this dimension. Such questions can be asked. Okay, not can be asked, will be asked. Even in JEE Advanced, there will be one question exclusively from dimensional analysis every year. So you should have this habit. Whenever you learn about any quantity, automatically you should derive its SI unit and dimensional formula. Okay. Anyway, what we have learned now is a formula which gives us the rate of emission of radiation by a black body. Okay, what are the factors on which it depends? Surface area and the fourth power of its temperature. Now, see, black body is the perfect absorber. In fact, it's a hypothetical object. It's 100% absorber. Okay, its absorptive power is equal to 1. It's the best absorber, you can say. A real object will not absorb as much as a black body. Okay, black body is a perfect absorber. Real objects are not perfect absorbers, so they won't absorb that much. We just discussed that good absorber is also a good emitter at a given temperature. That means a bad absorber is a bad emitter. Okay, like the object B here, it doesn't absorb much and it doesn't emit much also. Okay, good absorbers are good emitters, bad absorbers are bad emitters. Now, black body is the best absorber, then it should also be the best emitter at a given temperature. Okay, so when its temperature is T, black body emits at this rate, sigma A T power 4. Other objects will not emit that much because other objects are not such good absorbers as a black body. Then they won't be such good emitters as a black body also. Okay, so for other objects, dq by dt emitted by any object See, for a black body, it is sigma A T to the power of 4. Okay. For other objects, it should be less than this. To make it less than this, what we do is we multiply it with a factor, which is called E. E stands for emissivity. And obviously, its value ranges from 0 to 1. Okay. For a black body, E will be equal to 1 and the equation becomes sigma A T power 4. The expression on the right hand side becomes sigma A T power 4. For other objects, E will be less than 1 and the rate of emission will be less than sigma A T power 4. So generally, you can remember this equation. dq by dt emitted. Okay, that means rate of emission of radiation by an object. Any object, including a black body, is E sigma A T to the power 4. For a black body, E is equal to 1. Okay, note down this equation, all of you. This is rate of emission through radiation. Okay, rate of emission of heat, you can say. Okay, let's solve one direct question based on this. You know the rate at which heat is emitted means how much heat is emitted per unit time is given by this equation. Okay, so first question. Calculate total heat emitted by a cube of side, let's say 2 meters. Cube side is 2 meter. Emissivity, let's say, is 0.5. For a black body, emissivity is 1. For other objects, it is less than 1. Okay, let's say that it is 0.5 for this. And its temperature is 27 degrees C. Okay, it stays at that temperature, constant temperature. Fine. And I want you to find out total heat emitted by this cube in how much time? Let's say 10 minutes. Okay, you may use a calculator if required. And Stephen's constant, I'll write it here. Sigma is 5.67 into 10 power minus 8. Okay, watt per meter square per Kelvin to the power 4. So find out how much heat such an object emits in 10 minutes. First, understand what the equation gives you. dq by dt, rate of emission, means heat emitted per unit time, is given by this equation. And you can use this equation as it is if area remains constant for the entire time and temperature remains constant for the entire time. You can use this equation as it is for any duration of time. You can change it to delta Q by delta T if you want. Okay, total heat emitted by total time taken. If area and surface temperature remain constant, you can write it as total heat by total time also. Therefore, total heat emitted in a given amount of time becomes E. E is 0.5. Sigma we know is 5.67 into 10 power minus 8. E sigma area. Can any of you tell me how to express the total surface area of a cube?
6 times surface area of one
Okay.
side.
Cube has 6 faces. Each face is a square. Square area is length into length or side into side. So each face area will be 4 meters square and there are 6 such faces. So 4 into 6. 24 square meter is the total surface area of this cube. So E sigma A. Next, fourth power of temperature, that too in temperature in Kelvin. Now the given temperature is 27 degrees C. If you convert it to Kelvin, add 273, it becomes 300 Kelvin. So 300 to the power 4. I will write it as 3 power 4 into 100 is 10 power 2. If you raise it to the power 4, it becomes 10 power 8. Okay. So this is fourth power of temperature. You can multiply that with time interval as well, because on the left hand side in Stephen's law, you have heat divided by time. Now the question is only asking you what is the total heat emitted. So time goes to the other side. 10 minutes in seconds is 600 seconds. That is the time taken. And then you will get, like if you substitute it this way, you will get the answer in joules. All the given terms are taken in SI units, then the answer will be in SI units. Okay. Now this 10 power minus 8, 10 power 8 will be cancelled. The rest is just simplification. Okay. Using a calculator, you can do this. This way, you can find out the total heat emitted in 10 minutes or in any amount of time by any object. Okay. Understand what all you need to know. Had it been a black body, they won't give you emissivity of a black body. You need to remember that for a black body, emissivity becomes 1. Okay. And the equation becomes only sigma A T bar 4. It's not E sigma A T bar 4. Or you substitute E as 1. Okay. So this is how you use Stephen's law to tell how much energy is radiated by an object. Now, if you can tell how much energy is radiated, how much heat is released, you can tell the temperature change as well. Okay. But it's slightly complicated because, see, here we are assuming that for the entire time of 10 minutes, the temperature remains the same. Okay. That can happen only if it has a supply of energy also. If an object is only releasing energy without any supply, its temperature cannot remain constant. Okay. Then things become difficult. Okay. Then you will have to write it in this form, dq by dt. Okay. In a small time, how much is emitted? And okay, wait, we'll not even get into that. It's quite complicated. We'll do that, but not right now. Okay. Maybe next class or the class after that, we will discuss what to do if temperature is also changing. Okay, that we'll discuss later. So if temperature is constant, you can do it this way, right? Now, based on the body's temperature, okay, T here stands for temperature. Okay, not even body. This is the surface temperature. Fine, because finally or ultimately the emission from an object happens from the surface. Okay, molecules which are on the surface. So the rate of emission depends on the temperature of those molecules, the surface molecules. So depending on the temperature of the surface of the object, you can tell the rate at which it emits radiation. But objects will also be absorbing radiation, no? And there is a rate at which they absorb. Now, how much energy is absorbed by an object in a certain amount of time depends on how much energy falls on it, how much energy is incident on it, and where will energy be incident on an object from? From the surroundings. Okay, so how much an object absorbs depends on what the surroundings are emitting. Means it depends on temperature of the surroundings. Okay, so Stephen's law itself can be written in reverse. Means for absorption also you can write rate of absorption of radiation by a black body. dq by dt absorbed can be expressed as sigma A. See, absorption also happens from the surface only, no? The surface molecules are the outermost molecules of the object. They are the ones which receive heat from the surroundings, okay, which receive radiation from the surroundings. So dq by dt, the rate of absorption of heat through radiation is given by sigma A, temperature of surroundings to the power of 4. Okay, very similar equation to what you have for emission. In emission, T stands for surface temperature of that body itself. For absorption, we write Ts, which is basically temperature of the surroundings, because energy has to come from the surroundings to get absorbed. So you can use this equation for a black body. Now, black body is the perfect absorber, best absorber. Other objects don't absorb as much as a black body does. Okay. So for other objects, okay, wait, let me mention that this is for a black body. And in general, we can write rate of absorption is E sigma A Ts to the power 4. Okay. Uh, at the beginning of this chapter, this part of the chapter, or in yesterday's lecture, we discussed something called absorptive power. Absorptive power is the ratio of energy absorbed to the energy incident on a surface. For a black body is a perfect absorber. A will be equal to 1. Absorptive power will be equal to 1. And for a black body, emissivity is also equal to 1. Okay. A is 1, E will be 1. For perfect absorber, A is 1 and E is 1 because perfect absorber is a perfect emitter also. Now, other objects which are not such good absorbers as a black body will have A less than 1. Then their E value also will be less than 1 because we know bad absorbers become bad emitters as well. Okay. So remember generally that A is equal to E. Numerically, A will be equal to E. Absorptive power is equal to emissivity. E stands for emissivity. Okay. So the rate of absorption by any object in general can be expressed this way. E sigma A Ts to the power 4. You can also write it as small a sigma capital A Ts to the power 4 because numerically these two are the same. E stands for emissivity, A stands for absorptive power. For black body, both of them are equal to 1. For other objects, both of them are less than 1. Okay. So now we know how to write the rate of emission from an object. We know how to write rate of absorption from by an object. So you can tell how much heat will be released by an object. You can tell how much heat will be absorbed by an object also. If you can tell how much something is losing and how much something is gaining, you can tell the net loss or the net gain. Okay. For example, suppose an object releases some 300 joules of heat and absorbs 160 joules of heat in a certain interval of time. Then tell me, how much is the net heat loss from the object? It releases 300 joules, but in the same time, it receives 160 joules also. So, what is the net loss? I want answers from all of you. Type it in chat quickly. Okay. It has lost 300 joules, but in the same time, it received 160 joule. So, net loss will be whatever it has released minus whatever it has gained. Okay. Loss means what is going away, no? So, that will be 300 minus 160. That is 140 joules of heat. So, emitted minus absorbed gives you the net loss. If you want net gain, then you should do absorbed minus emitted. Okay, what we are receiving minus what we are giving away. That will give us net gain. Okay, simple calculations only. Fine. So from Stephen's law, we know that the rate of emission of heat through radiation is E sigma A surface temperature to the power 4. Okay, the body's own surface temperature to the power 4. And we know that the rate of absorption of heat is E sigma A surrounding temperature to the power 4. So we know the rate at which an object gives away heat and we know the rate at which an object receives heat. If we know both these, then we can write the rate of net loss of heat. That will be emission, means what we are giving away, minus what we are getting in return. So absorption. That will be the net rate of heat loss from an object. And you can write that as E sigma A is common to both the terms. Then T power 4 minus temperature of surroundings to the power 4. So that is the net rate of heat loss from an object. So This is like quite simple to understand. If you know the rate at which heat is going away and the rate at which heat is coming into the system, you can tell the net rate of heat loss from the system. Fine. Now, let me ask you one question. Suppose there are two objects, X and Y. Let's say they have same emissivity, means small e. Okay. Let's say they have same surface area. Okay. And let's say they are at the same temperature also. Emissivity is same, surface area is same, temperature is same. Stephen's constant is Stephen's constant anyway. For any object, you'll use the same constant. Okay. Now, depending on their temperature, they'll be emitting heat, right? They'll be emitting radiations. Let's not consider absorption. Let's say there are no surroundings. Okay. Assume these objects are far away in empty space. Okay. There are no surroundings giving energy to them. So these two are only losing energy. They are not gaining any energy. Okay. Both of them will be emitting radiations. Means both of them will be losing heat. If an object loses heat, what will happen? Its temperature has to decrease. Okay. Now the question is, will they cool at the same rate? Cooling, I mean, cooling at a certain rate. Cooling means reduction in temperature. Okay. So the question indirectly means, will their temperatures decrease at the same rate? Okay. Think carefully and answer. I'm telling you, consider only emission, don't consider absorption. So, due to emission, will they cool at the same rate? Is the question. Sohan, what do you think? Will their temperatures decrease at the same rate?
Yes, sir.
Can you justify why will that happen?
Sir, based on the formula, the rate of which they cool is dependent on E, sigma, A, and C, right, sir?
No, there itself you made a mistake. Okay, you can mute yourself. Yusuf, what do you think? Will they cool at the same rate?
So yes, sir.
Okay, how can you justify that?
So the formula.
Okay, can you tell the formula once?
So dq by dt is equal to
Okay, dq by dt emitted
yes.
is equal to
So E emissivity and then the symbols are 80. 80q, 80 to the power 4.
E sigma A t to the power 4. Okay, listen all of you. It was okay. Wait, I got one answer as no. Vijay Kalyan, why do you think it is no? Why do you think they will not cool at the same rate? Can you justify? Okay, fine. Let us discuss. See, it is given to you in the question that emissivities are equal. Sigma is anyway the same for any object. Surface area is same and temperature is also same. That means they must be emitting heat at the same rate. Okay, equal rate. But the question is asking you, will they cool at the same rate? That difference is what I wanted you to think about. Emitting heat implies cooling. Yes. But rate of emission of heat is not the same as rate of cooling. Okay. Notice this, all of you. Rate of cooling implies the rate at which temperature decreases. Okay. It is not exactly the same as the rate at which an object loses heat. Mathematically, rate of decrease of temperature is expressed like this: change in temperature per unit time with a negative sign. This is what is rate of cooling. Fine. Generally, rate of change of a quantity is written as dy by dx. So rate of change of temperature, if you want, d capital T by d small t. If you want rate of cooling, means you want rate of decrease of temperature, then it should be minus d capital T by d small t. That is what is technically rate of cooling. Okay. Now, according to the question, the rate of emission of heat is equal in the objects. Does that mean they will cool down at the same rate? We have to check. And we need to know the relation between heat and temperature to be able to relate them. If you want to relate rate of heat loss to rate of cooling, you should know the relation between heat and temperature. Can one of you quickly recollect and tell me how heat and temperature are related? We discussed this in calorimetry. How are Q and T related? Delta Q is equal to ms delta T, right? So for small changes, you can also write dq is equal to ms dt. Now in delta Q is equal to ms delta T, what does delta Q stand for? Heat absorbed by the object. Okay. And delta T is temperature change. Negative of heat absorbed will be heat emitted. So minus dq is minus ms dt. And now you divide by time on both sides. Divide by d small t, divide by d small t. This is how rate of heat loss is related to rate of cooling. I'll have to put ms aside, multiplied with minus d capital T by d small t. Okay. This is rate of heat loss. This is rate of cooling. That is how these two are related. They are not exactly the same. In between, there is that term m into s, where m stands for mass and s stands for specific heat. Now let's go back to the question. If mass and specific heat are same, then yes, rate of cooling, rate of heat loss will be same for the objects. Okay, I mean rate of cooling will be same for the objects. Now it is only told to you that they have same emissivity, surface area and temperature. Now emissivity depends on surface properties. If emissivity is same, means both of them have the same kind of surface. So material could be same. Emissivity same may imply that material is same. Of course, it's also possible for different materials to have same emissivity sometimes. Okay. Let's assume material is same because emissivity is same. Material is same means what? Specific heat will be same. Specific heat of X will be same as specific heat of Y. Okay, let it be. But there is another factor also, no, which is present between rate of heat loss and rate of cooling. This mass factor. What is the guarantee that the masses of these objects are equal? Just because surface area is equal, will that mean mass is equal? No. Okay. For example, consider two blocks like this. Two cubes, one empty cube and one cube which is completely filled. Definitely, if they are made of the same material, the one which is completely filled will have more mass. Surface area is same for both of them, but one has mass different from the other. Then it's not necessary that their rates of cooling will be same. Rate of heat loss is same according to the question because emissivity, surface area, temperature are same. So rate of heat loss will be same. But rate of cooling won't be same because mass need not be same. Okay. There is a chance that specific heat is different also. So the answer to this problem would be we cannot say. Unless we know everything about the objects, We cannot say whether they will cool down at the same rate or not. Had it been given to you that they are identical objects, then you can say. Okay. So I just wanted you all to understand and notice the difference between rate of heat loss and rate of cooling. They are not the same. Heat loss is needed to cool down. Okay. But technically, rate of heat loss is minus d capital Q by d small t. Okay. Rate of release of heat per unit time. Rate of cooling is minus d capital T by d small t. Means rate of decrease of temperature. And you need to know the relation between heat and temperature to relate rate of cooling and rate of heat loss. Okay. We'll solve more problems on this in tomorrow's class. So tomorrow's class will be about this rate of cooling, and we'll discuss problems in depth related to radiation. Okay. How an object radiates, how it like how much an object radiates, how much it absorbs. If both are happening simultaneously, what will happen? If there are two objects placed side by side, what will happen? Okay. For a flat sheet, how will the radiation happen? For a sphere, how will the radiation happen? Those things we'll discuss in tomorrow's class. Okay. Let's quickly go through what all we discussed today. We talked about, okay, first we discussed how a good absorber will also be a good emitter. Okay, from everyday experience, we can tell that. Then Blackbody is a perfect absorber, so it should also be a perfect emitter at a particular temperature. Then we talked about Stephen's law, Stefan-Boltzmann law, or Stephen's fourth power law. It tells how much energy is radiated by a blackbody per unit time based on its surface area and temperature. And for other objects also, you can write the equation. You will have to include that factor emissivity, which will be somewhere between 0 and 1. Then rate of absorption. Emission happens because of the body's own temperature. Okay, greater the temperature of the body, greater the molecular vibrations, greater the energy emitted by it. Absorption happens based on what is incident on the body. So absorption happens depending on the surroundings. Surroundings have to radiate, then object will receive energy. Okay, so rate of absorption depends on surrounding temperature. Okay, how to apply all these in problems we'll discuss in tomorrow's class. Right. Thank you all. We'll continue tomorrow.